Today, we're going to be developing a technique known as differential correction. This will allow us to take a given set of initial conditions, like the ones we found in the last lecture, and modify them slightly in order to keep our spacecraft orbiting the Lagrange point for a longer period of time. First off, I'd like to make a slight change in notation. I'm going to be referring to the position of the spacecraft several times in this lecture, and so I want to change our state variable to something other than x in order to avoid confusion between x the state and x the position component. I'm going to call our state c. You can think of c as standing for course or circle, even though our orbits aren't circular. The point is to give you some words that you can associate with c so that you remember what it stands for. So now we have c dot equals f of c. Note that there are many unique c of t that satisfy this equation. A specific c of t that satisfies it is one where c naught is equal to some specific initial state. Okay, with that out of the way, let's develop this differential correction technique. The technique comes from a branch of mathematics known as dynamical systems theory. Within dynamical systems theory, there's a body of literature for finding periodic solutions in dynamical systems. Here the word periodic means that for some period t, c of t plus big T is equal to c of t. Periodic does not necessarily mean stable. This could hold for a single period and then the orbit will diverge. So this isn't quite periodic in the sense of, say, a sine wave, but periodic in the sense that it can complete at least one orbit. We're going to develop a shooting method, and this is essentially the differential correction technique from Practical Numerical Methods for Chaotic Systems by Thomas Parker and Leon Chua. The technique is based on Newton's method for finding the roots of an equation, so I'd like to go over that first. Say we have some function f of x that crosses the x-axis at some point. Newton's method allows us to find the root by taking a guess and iteratively improving upon that guess. Let's call our initial guess x0. From there, we construct a line tangent to the function and see where it intersects the x-axis, and this is our new guess, x1. To find x1, we need to find the equation for the line. We've defined the slope as the tangent line to the function, or the derivative of the function. To find b, we use the fact that at x0 our function is equal to f of x0. So now x1 is merely the x value of the line when y is equal to 0, i.e. x1 is going to be negative b divided by m. So the new guess is the old guess minus the error, so to speak. You can essentially think of f of x0 as the error between the value of our current guess and our desired value, 0, divided by the slope at that point. Note also that Newton's method is numerical, meaning that unless our function is actually linear, we can't find the exact root, only an approximation, and it's up to us to decide how close of an approximation we want. When applied to a system of equations, we don't divide by the derivative, we left multiply by the inverse of the Jacobian evaluated at the guess point. Usually, in order to avoid computing an inverse, the system is rearranged as follows, so that we have a system in the form ax equals b that we can solve. So what does this have to do with taking our initial Lagrange point orbit and modifying it to stay orbiting the Lagrange point for a longer period of time? Well, if we can put that desire, the desire to extend our orbit around the Lagrange point, into an equation that's equal to 0 when our desired condition is met, then we can use this algorithm to find the conditions that make that equation true. There are actually a couple of different ways to do this, but I'm going to stick with how Parker and Chua do it for now, and then later we'll make some modifications. In Parker and Chua, they come up with the following equation. And before I introduce the equation, I want to introduce a new variable, q, which will consist of our initial guess for our initial state and the initial guess for our period. So now we'll call our equation h, and it'll be a function of q, and it'll look like this. So this equation is 0 when our particular solution for our given initial condition, c0, is exactly equal to c0 after propagating for some amount of time, t. So to apply Newton's method to this, we need to find the Jacobian of h, which is going to look like this, where this part is 6 by 6 and this part is 6 by 1, meaning we'll have a non-square Jacobian, which is going to be an issue, and we'll deal with that later. But for now, let's focus on finding these derivatives. How do we find dh dc naught? How does this function depend on changes in the initial condition? Well, one way is to do this numerically. We numerically integrate from C naught to C final. Then we add some small change to the x position, reintegrate, and we get a new C final. And so then the first column of our matrix is going to be, then we would do C naught plus some change in the initial y position, and so on. This means we'd have to integrate 7 times, once for the original C naught, and once for each deviation in the state. Is there another way to do this? Well, it turns out there is. Let's take a look at h and try to take the derivative with respect to C naught. The second term is simply the identity matrix. Now, let's take a look at this first term, and let's take a look at our differential equation. If we differentiate the differential equation with respect to C naught, find that we can take the chain rule on the right side and get the following. So what we have here, this term, is this term. And so we don't have an analytical equation for this term, but we have a differential equation for it that we can numerically integrate alongside our main integration. Note here that this term, the df dc, that's simply our A matrix from the second lecture. Except instead of being evaluated at the Lagrange point as we did in that lecture, we evaluated along the trajectory. Note also that dc naught, dc naught evaluated at time 0 is going to be the identity matrix. So now we have a differential equation and initial conditions that we can integrate. dc naught is usually written as capital Phi and is referred to as the state transition matrix. If you're interested in diving further into this, I wouldn't recommend using state transition matrix as a search term. You'll get better luck if you search for variational equation. So let's write out dh dc naught. Note that phi is 6 by 6, meaning that we now have to integrate all 36 elements of phi alongside the 6 elements of our state, meaning that we have 42 equations in total to integrate. Was it worth it? Instead of integrating 6 equations 7 times, we're integrating 42 equations once. In terms of performance, it might not be a big win if it's a win at all, but this is the canonical method used for finding periodic orbits, and we have no compelling reason to use the finite difference method instead. The eigenvalues of the STM can also prove useful for stability analysis, but we won't cover that in this lecture. Okay, let's talk about dHdt. This one's actually pretty straightforward. It's essentially the derivative of h with respect to time, but I'll show it graphically just to make it clear. Imagine we started at C naught, and we've propagated for some time t. And this gives us some value for h, call it h1. And now let's say we integrated the same C naught for some time t plus dt. This will give us a new h, let's call it h2. So now we know that the delta h is h2 minus h1. If we plug in for h, what we'll get is, if we then divide by dt on both sides, we'll get the definition of the derivative with respect to time on the right side, and so dHdt is simply c dot. It's simply c dot evaluated at time t. So now we can write our Jacobian and our system of equations. You might have been wondering, how do we get our initial guess for our period? Well, it's quite straightforward actually. We can just propagate our initial conditions until they cross the xz plane again, assuming we started from the xz plane. And SciPy gives us some handy tools to do that, but there are some other ways as well. You could simply propagate until you find some minimum value between the final state and the initial state, after excluding the initial part of the trajectory. What matters is that our guess is close enough to the actual value that we're looking for. How close is close enough? Well, as long as the algorithm converges, you're close enough. That's the thing about Newton's method, is that it can be vulnerable for, if you start too far away from the solution, you will eventually diverge and you won't find the solution. So if you start and your Newton's method isn't converging, it could be because you're too far away from the solution. So maybe try to see if there's a way to get a little bit closer. So now we need to address the issue that the Jacobian isn't square. It's 6 by 7, it's being multiplied by a 7 by 1 matrix to give us a 6 by 1 vector. It's essentially, we have 7 unknowns and only 6 equations. In Parker and Chua, they solved this by adding a constraint. We're going to do something similar, but we'll use a different constraint than the one they used. We're going to constrain our x0 value of delta c0 to be 0, meaning we're going to add a row to our Jacobian matrix consisting of 1, 0, 0, 0, 0, 0, 0, and also a row to the right side containing 0, reflecting our constraint equation delta x0 equals 0. This essentially means that as we update our initial conditions, our x position will not move. From here, we're ready to go into Python and write these things up in code and see how they work. As in the last lecture, I've already coded up some of these things in order to save some time. I'll briefly review that code, and then we'll get into constructing our algorithm. Okay, so now we're in Python. Like I said, I've coded up some of the relevant equations to save us some time, so let's briefly review what that code looks like, and then we'll get into constructing our algorithm. So here's the library. We saw this in the last lecture. We saw the system class. And I skipped over the equations of motion and the A matrix rather quickly. So the A matrix is the full A matrix that we derived in lecture 2, except instead of evaluating it at the equilibrium point, we've written it here in such a way that it can be evaluated at any point in three-dimensional space. As we integrate our trajectory, we're going to want to evaluate this A matrix for every point in our trajectory. Up here with the equations of motion, you'll see that when we are integrating the STM, we take the STM from our vector. This reshape here is just a technical operation because Python expects this to be in a vector, but the STM is a matrix, so we have to do this thing where we have a 36 element vector and then we bring it back to a 6 by 6 matrix. But anyway, here I just labeled X, Y, and Z instead of having just X's everywhere because I wanted things to be a little bit readable. And so we evaluate the A matrix at the position that we're currently at. X represents our current state. We multiply it by the STM, and that's our rate of change of the STM. And then we reshape that STM dot back into a vector. So let's go ahead and get back to Spider. And let's start constructing our algorithm. First, let's copy over some stuff from lecture 3, just to save us a bit of time. I think we're going to be able to copy, I think most of this, just before the station key thing. And we'll stick with the 10,000 case, and get rid of some of these extra ones. And I think we might need a plot later. Let's leave it for now. And then, just for the sake of making things look nice, let's just get rid of the 3 everywhere. Okay, so the first thing that we need to do is we need to come up with an estimate for our period. So to do that, we're going to take advantage of SciPy's events framework. An event is something that we can pass into solve IVP, and it's a function. And basically takes the time and the current state, and it returns a float. And then Python SciPy will find out where the time at which that event is 0. We can additionally add some properties to the event function in terms of whether or not it should stop integration and which direction we're going in. So in order to estimate the period, we want to stop integration as soon as the y position of the spacecraft crosses from a positive to a negative value. Because we start at y equals 0, and we start with a negative y velocity, so we go around. So to construct that, we basically need to return y1, and we need to set event.terminal to true because we want integration to stop then. And we want event.direction to be, let's take a look at the documentation. If direction is positive, event will only trigger when going from negative to positive. So we want it to go from positive to negative, so clearly we want direction to be -1. And then we simply pass this to here. There's one more thing that we need to do because this will stop immediately because y starts out as 0 and then it goes to a negative place. So we have to say return y equals 1 if t does not equal 0, else return -1. So here I'm just forcing it to return a -1 at the very start of the iteration. So if we run this, doesn't seem to have done quite what I wanted it to do. Oh, that's right, because we started at 10,000 y. Let's bring this and the z value back to 0. Let's try that again. Okay, that looks more like what I wanted. And so now we have our initial estimate for our period. So we have our C0, our initial conditions, and I'll note that here. I'm going to copy this because I'm going to want to compare it to the initial conditions later on. And now let's construct our algorithm. So actually, let's not worry about things for now. So the way we want this to work is we want to propagate C0 until time period to get CF. And then from CF, we'll compute H, CF dot, and the STM. Then, if H is below our tolerance, we stop our loop, otherwise we continue. In which case, we'll have to construct our Jacobian matrix from the STM, CF dot, and our constraint. Then we solve J delta Q equals -H, remembering to add our constraint to H. And then we'll just have C0 plus equals first 6 elements of delta Q, and then our period will add the last element of delta Q. And here we loop back to the beginning. So one more thing, because this is Newton's method, we need to both set a tolerance so that we can break here, but we also want to set a maximum number of iterations so that we're not in this loop forever. So let's write down our max iterations, and let's say we'll iterate as many as 50 times. And we'll need a counter for that. So here we'll go while counter is less than max iteration. And we're going to set our tolerance as well. So let's consider our tolerance. We want it to essentially be, for the position, I want our position to match our initial position to within a millimeter. And I'm going to use a Python trick. I'm going to say ×3. When you multiply an array times a Python array times 3, it'll actually give you 3 elements of the array. If you take a NumPy array, though, and you multiply it by 3, it does the somewhat more reasonable thing of multiplying the elements in the array by 3. But so we'll just use this trick real quick. And then for the velocity, I think it probably makes sense to be within a millimeter per second as well. So for that one, we need to do this, and then we need to multiply it by em.s. And again, we need 3 of those for each of our components. So we'll want each component of h to match each component of this tall vector. So okay, let's start with our algorithm here. So that's basically just what we have going on here, except some minor modifications. So instead of moving up to this, we integrate up to period, and we'll integrate up to C0, and we'll get rid of this event, because maybe we go a little bit past the period, that would be fine. And let's just call this trajectory, and now CF is going to be trajectory dot y, all values of it, and the last value. So now we have CF, and from here we compute H, CF dot, and the STM. So H is simply the first 6 elements of CF minus the first 6 elements of C naught. In this case, our C naught is going to be, it's only going to be 6 elements, and actually what we want to do for our EOM constructor, we want to say STM equals true, but now our initial condition needs to be a 42 element vector. So we need to basically concatenate our initial conditions with the 6x6 identity matrix, and we'll reshape that to be a 36 element vector. So far so good. Then we need CF dot. So that's going to be EOM's, basically just evaluating the EOM at CF. And then lastly, the STM is, it's the elements after the 6th element, and we want to shape this into a 6x6 matrix. Okay, so now we check our tolerances. So here we're comparing element by element, so I'm going to say all H is less than tall. So basically when I do H less than tall, it's going to give me an array of true false values, and I want all of them to be true in order to break. So now, assuming we didn't break, we will construct J from our STM, CF dot, and our constraint. So we're going to use a couple of things from NumPy here. We're going to use HStack to stack the STM, and we have to do something a little bit tricky with CF dot. Actually, first we need to make sure we do STM minus the identity matrix here, because that is our J. And then here we have to take the first 6 elements of CF dot, but NumPy is going to complain because this is a matrix, whereas this is a vector. So we need to do this thing where we reshape it to be a 6x1 matrix. So just a little technicality there. So that forms our 6x7 J matrix, but then we need to add our constraint. And so here we'll use VStack. So we're basically putting 2 matrices on top of each other with this one. And here we just do 1, 0, 0, 0, 0, 0, 0. Okay, so now we have our J, and so now we have to solve J dq equals negative H. So we'll do the same thing for H with adding the constraint, or not the same thing, we use concatenate. Here we have to pass 0 as a vector. But now we can say dq is equal to np dot Dynamical dot solve, and we give it J and we give it negative H. And so from here we have our C naught, and we take our first 6 values and we say plus equals the first 6 values of dq. And we have our period, and we say plus equals the last value of dq. And we also need to say counter plus equals 1 so that we actually get out of the loop. So one thing we need to do here, though, this is going to be a bit of defensive coding, but essentially we need to make sure that we reset the initial conditions, but that we reset the STM to the identity matrix here. So what we need to do is we need to say C naught after 6 equals np.I 6 reshaped to 36. So this is an issue I've run into a couple of times, where because we're keeping the state and the STM in the same vector, sometimes you forget to reset one and the integration starts where the STM is actually not equal to identity, and things basically just break. So with that, we should be good though. And let's see. So from here, what I'd like to do is let's bring these back. And whoops. So I'm going to solve using our C0. I'll get rid of the events here because I want it to go further. But basically, I want to plot this new solution and see what it looks like compared to my old solution. And one more thing I want to do before we do this check here, I'm going to print our counter, and I also want to print h, so that we get an idea as the algorithm runs how we're doing. So let's give this a shot and see what happens. So, okay, we went through 6 iterations before we reached our tolerance, and this is what we look like now. So this is what we looked like before. So now we've matched our initial state. And let's play around with this a little bit. So actually, I want to also plot the actual initial conditions. So I'm going to say IC0. Actually, I think we can do a little bit of Python trickery here. That bit of code right there will essentially expand IC2 into 3 values. And I'll make that blue, and let's run this again. So we have to sit and wait for our algorithm to run, but I'll fix that in just a second. So there you can see this is where we initially started. This was our initial position, and then the algorithm updated our initial position to be here. So let's quickly fix the slowness of the algorithm, and we fix that by switching to use the dormant prints solver. So this one is usually preferred in Nestor Dynamics because we want pretty tight tolerances. So you'll see if we run it, things went much faster. So we only took 3 iterations and they ran more quickly. And actually, let's go ahead and add this value here and here as well. And now our script should run quite quickly. There we go. That's interesting. The changing this to dormant prints changed our algorithm runtime. But anyway, let's go ahead and take a look at this plot in an actual 3-dimensional plot. So here we go. So if we look a bit closer, so yeah, we started actually pretty close to our initial position. And the important thing to note is that when we don't do any iterations of this algorithm, if I set max iteration to 0 and basically short circuit the algorithm and skip it, then it takes as little as not even 14 days before we're way off our trajectory now. So 14 was even a bit generous, perhaps even if I look at 10. Yeah, 10, we're not quite off our trajectory, but we're probably not going to stay on it for much longer. So yeah, at 11, you can already you got to squint a little bit, but you really start to see how we're not going to match up with our initial position. So we went from 11 days to now, if I bring the algorithm back in, and so we saw we were doing 28 days earlier. Let's try to do 35. So now at 35, we've started to diverge. Let's maybe go back a bit and see exactly where we started to diverge. So, okay, we can see some divergence happening at 31 days. It's not much, but it's there. You can sort of see it. There you go. That now we can see that there's some divergence. But this is pretty great. I mean, we started with not being able to stay in orbit around the Lagrange point for more than a week and a half, and now we've gone just about an entire month. And all we did is we made some very small changes to our initial conditions. So we want to compare this to the algorithm we developed in Lecture 3 for station keeping, but there's a bit of a problem. See, the problem is, if I take my new initial conditions and I compare them against my initial conditions, if you will, this is what it looks like. So our x position didn't change, which makes sense because that's a constraint we set. But the y position changed. It changed. How much did it change? So it changed by quite a bit, actually. It changed by 2 kilometers. And the speed's changed as well, but that's not what matters here. The problem is that for station keeping, we have to only be able to modify our velocity. So we can't just teleport a spacecraft to a new position, especially not 2 kilometers away, although even if it was a meter away, that would still be a problem. So we need to modify this algorithm a little bit in order to be able to use it for station keeping. So with that, we're going to go back to the notes real quick, and then we're going to go back into Python to finish up. So how do we modify our algorithm so that we can use it for station keeping? So essentially we'll need to modify our h function so that instead of being a function of the initial state and the period, it's a function only of the initial velocity and the period. Well, note that our initial state simply consists of the initial position and the initial velocity. So basically, we'll change our q vector to be v0 and t instead of c0 and t. So our h function remains the same. We're essentially just going to use the same initial position and just keep it fixed, but now our Jacobian changes. So dh dt is going to remain the same. dh dv0 is going to be very similar, but it's a little bit different. So let's take a look again at our differential equation. And let's do what we did earlier, and let's differentiate it with respect to v0. So once again, we have a differential equation for the quantity that we need, except it looks a little bit different because this is the same 6x6 A matrix that we had previously, but now this is a 6x3 matrix essentially. The nice thing though is that we don't have to change any of our equations of motion. When we finish the integration, we can essentially just take the right half of the state transition matrix. That's because the state transition matrix, when it's the derivative of the full state with respect to the initial condition, what we're really talking about here is we're saying that it's the derivative of the position with respect to the initial position, the derivative of the position with respect to the initial velocity, and the derivative of the velocity with respect to the initial position and the derivative of the velocity with respect to the initial velocity. So we're just ignoring these values. Note also that the initial condition for this thing would be a little bit different. Note also that when we take the full derivative of h with respect to v0, we're going to get dc dv0 minus dc0 dv0, and this one, instead of being the identity matrix, it ends up being a matrix, a 6x3 matrix that has 0 on top and a 3x3 identity matrix on the bottom. So this is a 3x3 matrix of zeros, and this is 3x3 identity matrix. And so now we have our full Jacobian. So now we can go back into Python and code this up and start comparing it to the algorithm from the previous lecture. Okay, so let's code up this velocity targeter algorithm. I'm actually first going to save this in a separate file, and then we'll make a new file where we'll do the velocity targeter so that we have this algorithm here by itself, because we need to make quite a few changes in order to make the velocity targeter work. So we'll save this as, and we'll go ahead and copy it and make a new one. Okay, so let's see, and we'll save this as lecture for part 2. So let's see, what are the changes that we need to make? So for the STM, we need to essentially take the last 3 columns of this. That's essentially going to be our DC dv0. Let's also make, so since we're not subtracting the identity matrix here, I want to make the matrix that we're subtracting right in here, so we do it outside of the loop. And I guess, oops, that should be DC 0, not DCO. I guess we can do a VStack on this one. So here we subtract DC not DV. And one thing that I forgot to mention last time is that with these changes that we made, J is now a 6x4 matrix. So we essentially have 4 unknowns and 6 equations. So we have more equations than unknowns, which means we don't need the extra constraint. And also, instead of solving, we'll have to do least squares. And least squares returns a number of things. It returns a tuple with a number of things, but we just want the first element of it. So this should work. Let's take a look. Let's see. Oh, that's right. C0, we're just impacting the velocity here. So 3 to 6 is 3 to 6. The rest should be fine. Let's try again. It's taking a while. It's not converging. Okay, what did I do? Oh, right. Instead of DQ 3 to 6, we want DQ up to 3. That should fix it. There we go. Okay. So yeah, this looks pretty similar to our previous result. This is going for 28 days, and we're still in our orbit. And let's see if this had any other beneficial effects. Oh, I'm changing the wrong variable. So yeah, if I run it again, yeah, so that looks like pretty similar result as previously. And if I let it go for, say, 35 days in the orbit, then it looks like we're still in there. And what if we went for a bit longer, let's say 40 days? So now we've started to fall off as before. So it's pretty similar result to the position targeter. So again, we want to actually do station keeping here. So what we want to do is we want to be able to integrate for a full year. And then while we're integrating, we want to be able to change our velocity. So we need to do a couple of things here. We essentially need to put this into a function so that we can actually call this and get a velocity back. So let's go ahead and do that. So it takes in an initial condition and a period, and we're going to have it return. Whoops, this should be period, not capital T. And it's going to return our C0 3 to 6 terms. So it's going to return just the velocity that we need. And okay, so now for this trajectory, we're going to want to integrate it for a full year. And I want to give it a max step of once per day, like we did with the other one, so that we have an apples-to-apples comparison. And get this down here so that we see everything. So on this one, I'm going to want to I want to make sure that we start in our initial orbit. So I'm just going to set this equal to velocity targeter for our C0 and our period. And just to avoid confusion between variables, I'm going to refer to this as C1. Not to say that it's, a time step later, but just to suggest that it's different from what's inside the function. It shouldn't actually have any issues, but I'd prefer to keep things a little bit separate. So, okay, let's just borrow from our station keeping code here. So this is essentially what our station keeping looks like. So we'll bring that into here. And so this one needs to change to C1. And instead of RK45, we're going to use dormant prints like we did before. Yep, this looks good, so we don't need this. So we have our initial conditions, we have our initial time, we have our final time, we have our max step, we have our tolerance. All this looks good. Y1 is of course C1. And on this one, I think we need to change this traj to simply empty since we're using Y. Don't worry about that one. We just need to copy over this line as well. And a couple other changes we got to make. Let's see. So new velocity is velocity targeter, and we take solver.y, and we want to take the first 6 variables, and of course here we pass in period 1. We're essentially just going to estimate the same period for each step. And so we have our new velocity and same, yeah, basically same stuff as before. So let's run this and see how it works. Whoops. What did I do wrong here? Nope, that's not good. I think I see the problem. We need to change this to be there we go. So that should fix that issue. Let's take a look. Uh-oh. Oh, that's right. I need an extra pair of parentheses around there. How about that? Okay, so now we got something going. This is taking quite a long time to run, and I think our issue is that it's running the velocity targeter at every stop. And we're going to change this so that it only runs it once per day, maximum. So we'll need to take care of last time the targeter ran. So if this is greater than a day, then we can do all these things. And just so that we can keep track of these things, I'm going to print the time. And this is going to be solver.t times em.s divided by 4 divided by 3600. So let's give this a try. Oh, and of course we need to set last time the targeter ran to be solver.t. Yeah, okay, let's give this a try. It's still not super fast, but at least we can see the progress. So this should just take another minute. Something appears to have gotten stuck. See, now our error is quite large. So it looks like what happened is that we fell off our orbit somewhere, and we fell off far enough that we weren't able to correct. So one way we can try to solve this is by reducing the requirement for when we burn. So we're doing 1 centimeter per second, which we got from the Artemis probes. I'll go ahead and make that 1 millimeter per second. So that's an order of magnitude less than Artemis, but I don't think we're breaking any, fundamental engineering, modern engineering constraints by going down to 1 millimeter. So let's take a look at this and see how it goes. Okay, so there we go. So you can notice there's a kind of a thickness to these lines. So, we're not hitting quite the exact same trajectory every time, but it's pretty close. I mean, this looks better than our initial result from the previous velocity targeter. let's take a look at how many times we've earned and what the sum of those were. So let's take a look at the sum first, and we need to multiply it by em.l and divide it by em.s to get our meters per second value. So that comes out to 30 centimeters per second. So that seems pretty good. And only 20 burns for the full year. So that's less than 1 every 2 weeks. So that seems much better than what we had previously. But in order to make sure the comparison is fair, let's run this guy. And I'm going to do a new console because I don't want to lose the data that I have in this one because it takes a while to run. So let's allow this one to go down to 1 millimeter, and let's also use dormant prints on this guy. So let's take a look at that. So yeah, the orbit's not as clean. You know, it's a bit jagged because dormant prints is just really good. But let's take a look at our all DVs. So this gets up to 90 centimeters per second. So that's better than what we had earlier. When we did this in the last lecture, this was up to half a meter. Sorry, that's 8 centimeters per second total. Before we had 50 centimeters per second total. But also if we look at the length, so that's 62 burns. So that's more than 1 a week. So we can see that the differential correction algorithm with the velocity targeter is already making some improvements to our algorithm, to our station keeping. So we're able to reduce the cost of station keeping in our model again, but in our model we're able to reduce the cost of station keeping by 1/3, by 2/3, and we're also able to reduce the number of maneuvers that we need to make. So one more thing that I want to point out before we go, and that's what happens when we add a z component to our initial conditions. So if I run this, I'll use a third console for this one. And I'll make sure to do matplotlib t. So if I run this, so it doesn't look like we're actually going up and down in the z. It looks like this is planar. And if we examine this, we'll see that as a matter of fact, the z component and z velocity are reduced to pretty much negligible values. You don't need to convert it between non-dimensional and dimensional units to see that this is effectively 0. So it's interesting that our algorithm sort of pushed out the z. So we need to make changes to the algorithm if we want to be able to have 3-dimensional orbits instead of just planar orbits. If you got it this far into the video, thank you very much for watching. Please leave a lowercase Greek delta in the comments. This guy, or this guy if you want. Again, thank you so much for watching, and I'll see you next time.